Okay, so now we're ready to carry on, and we're going to today take a look at measures of variability. Okay, now what's different here is that with measures of location, we were looking for the center of our data set. Now we're looking for measures of how spread out the data are from the center. So we need both of these in many cases. They're both very helpful. They complement each other very nicely. So it's important to understand how both types of measures work. Anyway, so these are the ones we'll be looking at. And you may have heard of some of these names before: the range, the interquartile range, the variance, the standard deviation, and the coefficient of variation. So we'll be doing these by hand, of course, and we'll also be doing these with Excel. Now, I just realized I forgot my calculator, so I'll be right back. All right, now we're ready. Okay, here we go. So the range is the easiest and simplest of all of the measures of variability. And I'm sure you already have a sense of what this is all about. All we have to do here is take the difference between the largest and the smallest values in our data set. Okay. Now, it's a very rough approximation. It's not the best measure of variability, but it's a good, easy number to calculate. If you don't need extremely precise information, the range can often be all you really need. So here they were going back to the example of the monthly starting salary, which we've been working with this data for a while. And so what they've done is they've organized the data from low to high, as you can see. And you can see that the smallest salary in our sample was 5710. The largest is 6325. So the difference between those two is 615, which is, of course, then our range. And that's all there is to it. By the way, I do want to mention here that as we've seen before, the range does not have, well, it has a formula, but um, it's not exactly it's not a numerical formula that we like with the sample mean, for example. And so the range is a process that is identical for both populations and samples. There is no letter or character of any kind that's used to represent the range. We just normally write the word range, and that's the end of it. So there's no symbol that represents the range. And as I said before, the range is very simply largest value in a data set minus the smallest value in the data set. Okay, so the next thing you notice is the interquartile range. Now, this one is a little bit different because this one directly involves quartiles that we looked at last time. Or if you remember correctly, the quartiles are actually specialized percentiles. Okay, so the first quartile, if you remember, is the 25th percentile, and that's simply the point below which we have 25% of our observations and above which we have 75%. Then we have the second quartile. It's the data right in half. Half the data are at that point or below, and half are above. Okay. And you also remember that this is just another name for the median. The third quartile is the 75th percentile, which means that 3/4 of the data are at that point or below, and then the remaining 25% are above that point. So the interquartile range is a very simple measure, and it's abbreviated IQR, and it's simply the difference between the third quartile and the first quartile. And that's all there is to it. Now, it may seem very simple and it can be very useful, but also we can use it in other formulas to get interesting results. We'll see later on how that works. But um, it's a very simple measure, but it can give us a lot of important results. But oh, and another thing too, the interquartile range is identical for samples and populations. All right. So far we haven't really seen any measures that are significantly different between samples and populations, but that will change very soon. Okay. So here they went ahead and they calculated the quartiles, which we did the other day. And they just calculated literally the difference between the third and the first quartile. And you can see the difference is 167.50. Now, this is one of the more important ones, the variance. Okay. So now we're getting into some very deep waters here. The variance is a very complex measure, and you'll see that in this case, it is different for samples and populations. So, what exactly is this variance all about? Well, it's hard to describe in English, but what you're effectively finding here, average square distance from each observation in a data set um, to the center. Okay. In other words, if you could imagine that you've got all these observations, um, I guess we could draw a graph here. Let's say your data are laid out like this. Here's 5, and here's 7, and here's 9. And let's just say the center of our data is 11. So what we're trying to capture is how close are these points on average to the center? Are they very close? Are they very far away? And that's really what you're trying to accomplish. So if you could imagine, we had a bar chart for two different samples, let's say. You could see at a glance which one has the largest variance. So let's say we have this situation. So remember how bar chart works. Each of these bars is a single class, which could be a range of values or a single value. And then the heights of the bars are the frequencies. So here, the values are quite close to the center on average. And so let's say we have this case instead. You can see in the right-hand side, the data are pretty far spread out. So on the left-hand side, in this sample, the data are on average very close to the center. Or the mean. Okay, in other words, we're specifically talking about the mean here. Actually, I'll tell you what. Let's make this a little more clear. Let's call this sample one and sample two, just so there's no doubt about what we're doing here. Okay, so in sample one, they're all pretty close to the center. How about two? Okay. In sample two, the data are much more spread out. Sample one. Therefore, the variance of sample two is greater than the variance rather, of sample one. So you can tell just by looking at these histograms that the data are very close together in sample one. They're pretty far apart in sample two, so clearly the variance is much higher in sample two than in sample one. Now, of course, you can only get so much information out of a graph. So that's why we have numerical measures. So of the variance makes it possible to directly compare um, how much variation there is in different samples or populations. So I can compare them side by side without having to look at graphs. I can look at numbers, and that makes it much easier for me to compare them directly to each other. Okay, now the variance has a slightly different formula. Populations and samples. It's a very subtle difference, but it is important. And so we're going to start by introducing the oh, well, they have them both listed right here. How do you like that? So on the left, we have the sample variance, and you can tell because it's represented with the letter S, a Roman letter. And we remember we've already discussed that sample measures are described with Roman letters, while population measures are described with Greek letters. Okay, so this is the sample version right here. And then the population variance looks like this. It's better. Okay, so let's take a look at these variables. Now you can see they have a lot of terms in common. So in the sample version, you have the sample mean. Now this xi is a single element of the sample. N is the sample size. So what you're doing is you're taking the average, like I said, squared difference between each element of the sample and the mean. You square them and you divide by the sample size minus one. And that number is your sample variance. On the right, we have something new here. This is the Greek letter sigma. By the way, I do want to point out here that there's two different sigmas floating around here. We know that the summation operator is also sigma. So what gives, how can that be? Well, this is the uppercase version, and this is the lowercase version. They're both sigmas, but one is uppercase and one is lower. All right. So we need a Greek letter to represent the population variance. And also, if you notice, once again, we see here mu is our population mean. And then they're going to use capital N here to represent the population size. So you can tell them apart. Okay. Now, the only difference algebraically between these two is right here. So in one case, you're dividing by n, the full population size. In the other case, it's n minus 1, the sample size. That's the only difference. But it is an important difference. So it's important when you're working on problems like these that you make sure you know whether your data represent a sample or a population, because if not, you're likely to get it backwards and you'll get it wrong. So if you're going to MindTap and you keep typing in your answer and you think, well, what's going on here? I think I have it. You might be using the wrong version. Okay. That happens a lot in the early days of statistics. So anyway, let's do an example. Oh, I guess before they do that, they wanted to introduce us to the next measure on the list. There's a reason for that. These two are actually directly related to each other. Um, it turns out that the standard deviation is the square root of the variance. Now, you're probably thinking, well, why do we need to do that? The variance has one major shortcoming. It is measured in squared units. So, in other words, for example, if the sample consists of prices from different stores, the variance is measured in dollars squared. Now, of course, there is no such thing as a squared dollar. So the standard deviation is the square root of the variance and is therefore measured in the same units as the data, which in this case would be dollars. So the standard deviation is just a way of making the units more convenient. It's the same principle. You're still calculating the distance between the elements of a sample or a population and the mean, but you're doing it in a different way. Okay. So the two of them, once you know one, you automatically know the other. They're not two separate measures. Okay. So that being the case, the formulas, as you can see, will represent that. Here's the sample standard deviation. And here we'll have the population standard deviation. And let's take a look at them. And it should be no surprise to see that you just take the square root. Okay, great. So now I'm sure they must have an example waiting for us. Here we go. Well, maybe not. We'll get to that in a minute. Now, if you notice, there's one more measure on our list. If you go back to that slide that has all the measures of variability, the coefficient of variation is less. This one also is a function of other existing measures. So what that is all about is that the coefficient of variation represents the variability of a data set relative to the mean. So it's written like this. Base. All right, so the sample version is this one. Okay, so you notice what we have here. We have the sample standard deviation divided by the sample mean. We then usually multiply it by 100 to turn it into a percentage. For the population version, instead, we have this. All right, so and again, you can see it's variability versus mean. All right, so how spread out are the data relative to the mean? Okay, now for some applications, it's easier and probably better to use this measure than either the variance or the standard deviation. It depends on what you're looking at. But for some applications, this is probably a better way to go than these two measures. Like for example, stock returns. Okay, so here's a quick example. Suppose that stock A has a mean or average return of 10% per year, and its standard deviation is 20% per year. Stock B has a mean or average return of, let's say, 20% per year, which is sounds great, but its standard deviation is 50% per year. Now, you might look at the two and say, well, I would definitely want B. I mean, who wouldn't want B? It's got the higher return, but guess what? It also has a lot more risk. So the standard deviation of the returns to a stock is often referred to as the stock's volatility. You'll see this when you get to finance class. And volatility represents the risk of the stock because a higher volatility indicates that the returns change more rapidly over time. So in this case, the coefficients of variation for the two are for A, and by the way, we're assuming this is sample data. So your standard deviation is 20. Um, the mean return is 10. Multiply this by 100, and you get 200%. For stock B, you're getting, wow, 50% is your standard deviation. That's a very volatile stock. You are getting a higher return, of course, but you can see here's the problem. So yes, it's true that stock B has a higher average return, but its risk, as measured by the standard deviation, more than twice as high, or as great as for stock A. So in other words, for stock B, each unit of return leads to 2.5 units of risk. For A, it's only 2 to 1. So in principle, unless you're a gambler, investors would prefer stock A. Okay, because your risk is only twice as great as your return, whereas for B, it's 2.5 times. Okay, so you can see rather than just looking at the returns or just the variances or standard deviations, this way you can look at both at the same time. So this can be a very helpful measure depending again on what you're trying to compare. For other cases, this isn't really that important, and you might just want to directly look at the means or the standard deviations. All right, so we have actually this is it for our measures of variability, but now we have to figure out how to implement them. So Now they're going to have us go back to the monthly starting salary spreadsheet. So we're getting a lot of mileage out of that one. So here it is again. This is the original one without all the results we had last time. And they're going to ask us to calculate the sample variance, the sample standard deviation, and the coefficient of variation. All right, well, we can do that very easily. So we'll do, and again, we're assuming this is a sample, which is usually the case. They want the variance, the standard deviation, and the coefficient of variation. Now we have a couple of options here. Since we're doing it in Excel, we could actually do all the algebra ourselves, but that's not really necessary because here's what you can do instead. Excel has these functions, well, two of them built into it. Um, so the variance is calculated as, now the formula here is called VAR dot S. Now this is how Excel sets this up. It has a variance formula for both samples and populations. In fact, I'll type this in over here. Okay, so the dot P or the dot S tells you whether it's a sample or a population. All right, so let's do this. So it's VAR dot S for this data set. Now the standard deviation, you have two options here. You can use, now this is spelled, by the way, stdev dot S. Okay, so use stdev dot P for populations, stdev dot S for samples. But we could have, in fact, let's do that here. Let's have a second line here just to show that they're going to give us the same answer. Just do the square root. That also works. And then the coefficient of variation, it doesn't have its own. So what we will do is we'll need the average or mean. And then, as we saw here, the coefficient of variation is the standard deviation over the mean times 100. So we know the standard deviation. The mean, we haven't calculated it yet, so we have to do it right here. And then multiply by 100. Oops, I missed one of the parentheses. Uh-oh. Oh, I'm sorry. I just realized, what am I saying? It's average in Excel, sorry. There we go. Now we're good. Now, it's a very small number because the salaries are, in the thousands. And so, but it's 2.788. And so, rounded it. This one. Huh, I got a slightly different number. That's interesting. What is the, wait a minute, hold on a second. I think there might be a typo in the slides. Yeah, you see what happened here? They've got 3940. It should have been 5940. So we have the right answer and they don't. All right, I don't know if you noticed that. This is a typo. So yeah, it's actually 2.78%, not what they have, which is 4.2%. Okay, so this is how we use Excel to get to those results. And Of course, now the important thing is, although they never explicitly said so, this is a sample. So just be aware that if you'd chosen to use the population formulas, you would have gotten something a little different. All right. So, and here they have all the formulas. And so that's it for 3A. So we just basically completed all of the measures of variability. And so now we're ready for part 3B, where we'll be looking at ah, well, we're going to be looking at other graphical techniques for representing our data, but we're also going to introduce two new measures that are designed to help us understand the strength and the direction of the relationship between two variables. Okay, so those are referred to as measures of association. So we will know three types of measures: measures of location. Let's make a note of this here. So we now know what they are. I mean, these first two, we get it. The measures of location, the mean, median, mode, et cetera, tells us the center of the data. The measures of variability tell us how spread out the data are from the center. And then this new one, these are called measures of association. And these, as we'll see in a bit, show the strength and the direction of the relationship between two variables. In other words, are they closely related to each other? Are they not very closely related to each other? That type of thing. All right, so let's see what they've got for us here. So I think they're going to introduce some more graphs. Um, skewness. Now this could be very important. Now remember, we did briefly mention this before. If you have a histogram of data like this, remember, this is the case where the data are symmetrical about the center, meaning the left and the right are mirror images of each other. So this measure, which doesn't fall into one of the categories we've already described, this is something a little different. This measure is called skewness. And Excel does have this measure built into it, by the way. So skewness is designed to show whether a data set is symmetrical about the mean, negatively skewed, or positively skewed. So the measure is designed to make it easy to interpret it. If a data set is symmetrical about the mean, the skewness measure equals zero. It's so simple. If the data set is negatively skewed, we can see where this is going. The skewness measure is negative. If a data set is positively skewed, the skewness measure is positive. It's pretty straightforward. Okay, the formula itself is quite messy. In fact, if you want, we can go back in here and apply it to this data set. Um, I'll tell you what, I wonder if we could ask it for a bar chart when the data are not sorted. Let's find out. Oh, no, but that's not good because all it did was list them all separately. Um, what I'm going to do is sort them out. And the way you do that is data, sort by column E from low to high. Great. So I suppose we could create some classes here. Let's say, oh, I don't know, 5700 to 5800 or 5799, that would be. And then you have 5800 through 5899, 5900 to 59. All right. And then you would have to type in the frequencies, and then we could create a bar chart. So let's see, what do we have here? All right. So let's do a bar chart from this. And, it kind of looks like this data is skewed to the right just by visually looking at it. So, but it's hard to be sure. That's why we like numerical measures. Graphs are wonderful, but sometimes, you need the precision of a numerical measure. So what we're going to do now is calculate the skewness of this data and see what happens. The command is called skew, and they do not make a distinction here between samples and populations because you'll get the same number. So it is positive. Now remember, the benchmark is zero. Zero would mean perfectly symmetrical. So the mere fact that it's positive means that our instincts were correct. The data are positively skewed. All right. So that's kind of nice to know. And that also means that if we had another set of data, we could see which one is more skewed or which one might be skewed to the left. So it's easier to compare them directly with each other as opposed to simply looking at graphs, which are very difficult to compare. So here, yeah, so this is what negative skewness would look like. And by the way, this is something we didn't mention before because we hadn't encountered these measures, but when a data set is symmetrical about the mean is equal to the median. When a data set is positively skewed, the mean is greater than the median. And when a data set is negatively skewed, the mean is, well, the mean is less than. We could write it in a couple of ways. The mean is less than the median. So why don't we go back here and calculate the median of our data set and see if this works. So the mean is 5940, and that is greater than the median rather. So the mean is greater than the median since this data is uh, positively skewed. Okay, Now, sometimes the skewness itself, like this one is the tail is quite long, so the skewness goes up. So if it has a very long tail, the skewness gets larger. When the observations are closer to each other, the skewness is not quite so large. Now, here we have something, we'll run into this again later on in the course, something called z-scores. So this is something, like I said, we'll see a lot more of this later on in the course, but a z-score is a measure that shows how large a measure is, a number is, I guess, rest of the data set. Now, this is based on a very specific distribution of the data. If you can visualize a bar chart that looks like this, nice symmetrical bar chart. All right, it's not perfect, but you get the idea. So anyway, this represents something we'll see way later on in the course, the so-called normal distribution. So what is it meant to do? Well, what if I am giving out an exam, let's say, and with z-scores, the center is 0. And then you might have, let's say, a 1 here, a 2 here, -1, and -2. So if your score in the exam is 2, your z-score is 2, that means you did really, really well. You did better than the overwhelming majority of the class. If you got a -2, you're in a lot of trouble. Okay, so the z-scores, the beauty of the z-scores is that they will be the same regardless of the mean or the standard deviation of this data. So I could compare these results for two different classes, let's say, more easily than the actual numbers themselves. So it's a way of turning them into a standard scale that is easy for me to determine how far away I am from the center and the likelihood of actually getting those numbers. So again, this is something we'll have a much deeper discussion about this later on in the course. But for now, it's enough to note that all you're doing here is you're taking x minus the mean, which if it's a sample would be x bar. And then down here you have your standard deviation. And that's where these numbers are actually coming from. So regardless of what the test scores were, once I standardize them, they're going to look like these z-scores. So just as an example, what if I told you that for this particular test, you have a mean x bar of, let's say, 80, and the sample standard deviation is 5. So if somebody gets a score of 90, so somebody in the class gets a 90, where do they stand compared to everyone else? 90 is your score minus 80, the average over the standard deviation. Two. So there's, you can see from the graph that that's a fantastic score. You did more than better than, let's say, 90. The actual value, I think, is 93%. But anyway, so a z-score of 2 means you did fantastically well. Whereas, let's say you got a 70, then this time you have not such a successful score. Pretty rough. You're way down here somewhere. So in other words, it gives more meaning to, let's say, the data. In other words, I can tell by looking at it, how is 70 a good score? Is it a bad score? Once I know my z-score, then I can tell where I stand compared to the rest of the class. So that's why these are very useful. But of course, it's based on the assumption that the data are distributed like this. So if not, then we have to use something different. So you'll see a lot of that in statistics. Now, they do have an example here for us. So they're going to give us this data. Now, I don't think they gave us a spreadsheet. I'm just going to type it into Excel. I'll just call it Z scores. Let's try that again. I made a ridiculous typo. I'm going to start that spreadsheet again. Okay, much better. All right, so here's the numbers they're giving us. Actually, I can copy this directly. Oh, ooh, maybe not. Sometimes you can and sometimes you can't. I guess it depends on how they copied and pasted this. So we'll create our own version of this. Now, I think I told you last time how to make the columns look nice. Just use the wrap text command. Yeah, that's better. Deviation about the mean. Oh, I guess I need to do that again. And then this will be my z-score. So first we have 46, 54, 42, 46, and 32. So I think now they're giving us the mean and standard deviation, but I just want to confirm. And the standard deviation, remember, is stdev.s. Oh, yeah. Okay. 44 and 8. Beautiful. So the deviation means how far away is it from the mean? So you take this number and subtract the mean. Now remember this little trick. I don't want this cell reference to change, so I'm going to use dollar signs when I type B7 so that I can drag this down without typing it 5 times. So this is the numerator of the z-score formula. So I'll put it in here. And then the denominator is just the standard deviation. So I'll take this number and divide by the standard deviation, which again, I'll use dollar signs to represent because I don't want that reference to change. Okay. So in other words, this is an unusually large class here, and this is an unusually small class here. So we interpret that as 0.25 standard deviations above the mean, 1.25 standard deviations above the mean, 0.25 standard deviations below the mean, 0.25 standard deviations above the mean, and then finally 1.5 standard deviations below the mean. I think that's all they're going to say. Now, Chebyshev's theorem is a theoretical result. It basically tells you how what proportion of our data set will be within some given number of standard deviations of the mean. Now, this theory is useful when we don't really know what the underlying data look like. In other words, we don't know what the properties are. Normally, you wouldn't use this because it gives very only approximate results, but I think they may ask you about this in MindTap. So based on what it's telling us, this you can remember this chart here, 13. It's telling us that at least 75% of the data must be within two standard deviations of the mean, 89% within three, and 94% within four for any data set, no matter what kind of properties it has. So here we have using, now this is Chebyshev theorem. Suppose that midterm test scores had a mean of 70 and a standard deviation of 5. What's the number of students having test scores between 60 and 80? So we're not thinking about the, actual number 20. We're thinking in terms of standard deviations. Okay, so 60 would be, let's write this into the notes. Let's say that, we have 100 students. The mean is 70 and the standard deviation is 5. And they're trying to figure out how many students are in between 60 and 80. So the 60 is two standard deviations below the mean. 80 is two standard deviations above the mean. And we just got through seeing that according to Chebyshev's theorem, being within two standard deviations of the mean has a probability of 75%. And since there's 100 students in the class, and according to Chebyshev's theorem, 75% should be within two standard deviations of the mean, then there should be 75 students with scores between 60 and 80. Now, we don't know if that's actually happening, but theoretically, that's how they should be. 75% or 75. Now here, this is a different one between 58 and 82. So if you can see, this is within 2.4 standard deviations of the mean. Now they have a formula here. This is what this is all about. If you don't have an even number of standard deviations, two, three, or four, you can use this formula. So 58. And by the way, how do you figure this out? Well, if you take that formula we had earlier, so in other words, we use that formula to tell us that 58 is 2.4 standard deviations below the mean. And the other one they wanted was 82. Well, it's the same thing except it is positive. So in other words, what they're telling us is that 82 is 2.4 standard deviations above the mean. So now we don't have a rule of thumb for 2.4 like we do here. So what you have to do is take this formula 1 over 1 minus z squared. A given number of standard deviations of the mean. Okay. Now it has to be the same above and below, right? That's one of the drawbacks of this formula. But if z is 2.4, so 2.4 squared is 5.76. 1 over that is 0.1736, and that leaves us with 0.8264. 82.64%. And so they're telling us, Chebyshev is telling us that that's how the percentage of the class that should be between 58 and 82, because that's 2.4 standard deviations away from the mean. Now, the empirical rule is actually taken from the normal distribution. We're going to see more of this as we go along. And it does say, yeah, we're going to see this in chapter 6, so don't worry about it. But this is only an approximation to the normal distribution. And so the normal distribution looks like this. It's a bell-shaped curve. And so you can imagine that. Oh, and by the way, if you notice, it is symmetrical. So the z-scores will look something like this. This is one standard deviation above the mean. This is one below. This is two above. This is two below. This is three above, and this is three below. So they're telling us that the empirical rule is that, which, by the way, is different from Chebyshev's because it's based on a specific assumption, so it's a little bit more precise. 68% are in this range within one standard deviation. is 95. I'll use different colors for that one. Okay. Um, and then within three, which I'll make that, let's say, green. Well, it's a bit of a mess, but so in other words, to summarize it, um, according to the empirical rule, 68%, and that would be of the elements of a data set, are within one standard deviation of the mean. 95% of the elements of a data set are within two standard deviations of the mean. And then 99.7 are within three. Assuming, now this is the difference between this and Chebyshev. Chebyshev's theorem, this rule is based on the assumption that the data set is normally distributed, meaning it follows the bell-shaped curve. Chebyshev's inequality theorem is not based on any assumptions. So if we know that our data are normal, we can use this rule. But if we don't, we can always use Chebyshev. Outliers. Now, what in the world is an outlier? An outlier is a member of a data set that is either much larger than or much smaller than the other elements in the data set. All right, so like here's an example of this. Suppose that a retiree decides to go back to college. They never went to college and they always regretted it. So now they just turned 70 and they think, well, you know what? I've got all this time in my hands. Why don't I go back to college? Um, the retiree's age in a college class will be an outlier since the rest of the class is likely to be between, let's say, 18 and 21 years old. So then you've got the one person sitting there who's 70 and saying, whoa, college, I finally made it. The rest of them are 18 to 21. So in that sample of students, the retiree's age would be the outlier. But you never know. Like it could go the other way around. There could be a number in there that's very small. Um, like, for example, suppose that a gifted student enters college at 14, let's say. It does happen once in a while. His or her age will also be an outlier, although it's not that far off from the others, but still it's quite low. An outlier within a college class. Now, here's the big question with outliers. The thing is, it's hard to be sure when something is and is not an outlier. We need a specific set of guidelines determine if a number is an outlier or not. Sometimes it's obvious and sometimes it's not. Like it's just, it's sometimes you don't want to have to rely on judgment. Let's put it that way. So there's a rule that will let us figure out whether or not um, an observation is an outlier. So in this particular case, the rule that they're going to use is any element of a data set that is at least three standard deviations above the mean or three standard deviations below the mean. Because if you look at this graph, the normal distribution, you'll see that three, that's way out there in the tail. To be out here or down here, that's not very common. So we're going to think of those as outliers. They're so far out that there are at least three standard deviations above the mean or three below. Now, outliers can cause a lot of issues with our results. So it can be important to detect outliers. Now, like in this set, there's no outliers because nobody is at least three standard deviations above the mean or three below. Now they do have these special graphs. I don't know if you're going to be asked to do this in MindTap. I don't think Excel has the ability to create these graphs. This is one way in which they seem to have left this out. This special type of graph, the five number summaries and box plot, it's there to show us, besides the three quartiles, it has the smallest and the largest values in our data set. So for the going back to the monthly starting salaries, we could easily figure that out for ourselves. Here we go. So let's take our data again. We'll move it somewhere else. Let's say over here. It doesn't matter if it's sorted or not, by the way. Actually, I'll just grab this. We're going to do exactly that. We're going to find five things. Oh, actually, we don't need this. Minimum, first quartile, median, third quartile, and maximum. And those are going to give us some insights into the properties of this data set. So the minimum is easy in Excel. It's just min. First quartile. Now remember, it's got to be quartile.exe to match what they're getting in the slides. And it's going to ask you which quartile. That would be one. Then the median is easy. That's the second quartile, but we can also just say, what's the median? Third quartile, same thing, quartile.exe. Here's our array of data. And we're going to ask for the third quartile. And then finally, we're going to ask for the maximum, which is simply max. That's it. So then this graph that they're going to have us do, what do you have? Let's make sure we got the same numbers. 710, 58, 57, 50, 5905, 60, 25. Yeah, we got the same numbers. Good. So This is the box plot. Now, by the way, I just want to point out here that they're using a different definition of outliers here. Um, that's again because we're not assuming that this is normally distributed data. So when we don't have necessarily normal data, one way we can do this is to do it like this. We can use the following definitions for outliers. So any value that is above 1.5 times the IQR, which is the interquartile range, or more than, I should say, third quartile, or any value that is more than first quartile. So in other words, 1.5 IQRs above the third quartile or 1.5 IQRs below the first would represent outliers in this case. So we could do that here. So first, the interquartile range is simply the difference, as we saw before, between the third and the first quartile. So now they're calling it the lower and the upper limit here. Anything above the upper limit or below the lower limit is an outlier. So the so-called lower limit is the mean, the first quartile minus 1.5 times the IQR. The upper limit is 1.5 times the IQR above the third quartile. Okay. Oh, let me change that slightly. Just to be consistent. All right, so once again, this is the first quartile minus 1.5 times the IQR. This one is the third quartile plus 1.5 IQRs. So if any of these values are outside that range, they would qualify as an outlier. Now it's going to be hard to see this unless these are sorted. So I'm going to sort them right now. So we'll have from the data tab, data sort from low to high. So the lower limit is 5606. We don't have any outliers that are too low. 6276 right here. This one is an outlier. Okay, so we do have one. That means somebody's getting paid very, very well compared to everyone else. And this graph is meant to represent that. So like I said, I don't think they'll ask you to deal with this in MindTap because I don't believe Excel has the capability of drawing this thing. Okay, so now we're ready for those measures of association. Now, this is a fairly complicated topic, so I think it would be best if we save this for our next session because we've gotten a lot done today, but this is something that's going to take a while to get through. So we'll save that for next time, and I'll see you then.